Hello, good time of day, everyone, and welcome to a new MLIR meeting. Today, Mathieu is going to present a new project which will allow to define operation, dialect, type, attributes, all at runtime, which will dramatically increase the extensibility of MLIR. Mathieu, we are looking forward to hear.
Hi, everyone. So I'm Mathieu, a PhD student from the University of Edinburgh. So what I'm presenting you today is, as Mehdi said, a tool to define operations, types, attributes, and dialects at runtime. So what's the motivation here? So currently, like in MLIR, the operation and types can only be defined at compile time. So what do I mean by define here? I mean that if you take a simple example of an operation defined in TableGen, what I mean defining is setting up the name, so here constant, setting the arguments, saying the number of results, defining the verifier, the printer, and the parser. So when I say defining an operation, that's what I mean. So currently in MLIR, everything is defined mostly at compile time. But defining operation types of dialects at runtime would pretty simplify the way user could define operations with things like metaprogramming, or define operations with a configuration file, for instance. So what you can have, what already exists at least, in the linear dialect, if I recall, or define operations from another language, something like Python, which I often see questions pop up in discourse or in Discord, for instance. And all of that without the need to generate C++ or without the need to recompile MLIR. So there is, with this presentation, I'm going to also send an RFC tomorrow on the discourse channel on what I call extensible dialects. So the idea is to extend the dialect class with what's called an extensible dialect that would allow you to define operations and types purely at runtime. We also, this way, we also, with this RFC, would allow the definition of traits and dialects at runtime with the MLIR context. And the first patch should be ready tomorrow, and send on Fabricator tomorrow, and we'll add the dynamic operations and types. So for that, what I mean by defining operations at runtime, I will just go through a simple examples. So we will assume that we have already a math dialect, and we want to add support for complex numbers, for instance. So we want to be able to pass and print this MLIR file. So what's important here is that we want this thing that is like in bold. We want to have a new type, the math.complex type, that is parameterized over another type. So here it will be a complex number composed of F32 and another F32. And we want to create the make complex operation that creates a complex number given a F32 and a second F32. So for that, we first need to make what I call a dialect extensible. So let's say we had in TableGen already a dialect like a math dialect. The way we would make it extensible is currently just, is with dispatch, we just set a Boolean to 1, the is extensible. And this will create all the support we need to create to define operations and types at runtime. So also as a note, we could technically make all dialects extensible by default, but that might increase too much the compile time of MLIR or things like this. I just want to set extensible the dialects we want, so we don't have to have it too big of a cost whenever we want to do that. We can also create, if we want, new dialects at runtime. So as I said, with dispatch, if you take MLIR, the MLIR context, you can create a dynamic dialect with just a name. So here it will directly create a new dialect at runtime because we haven't created like a class for the dialect or whatever. And we can get it with just its name. And this dialect will directly be extensible. So now that we have made extensible the dialect, we can create a type, so the math.complex type. So to create a dynamic type, so whenever I say dynamic type, it means types created at runtime. So we need to give it a name first. And the name will be used for the parsing and the printing of the type, as well as when you want to look up a type in a dialect. So for instance, if we already registered the complex type, we could get it with the function getDynamicTypeDefinition that exists in the dynamic dialects, in the extensible dialects. So the dynamic types are always parameterized by attributes and can define a verifier. So we can write a verifier so we can create this verifier function that will take as for argument something to emit an error in case the verifier was not satisfied, and a list of parameters that correspond to all the parameters you have on your type. So here, in our case, we want to create a complex type, but is parameterized by only one type. So we need to check that there is exactly one parameter, and we need to check that the parameter is a numeric type. And as a side note, the verifier is a unique function. So here we can actually capture runtime information. That's why it's kind of important to have like runtime operations defined in runtime. So we can define also, to define this type, we also need or can define a custom parser and a printer. So this is exactly how you would define a parser and a printer currently in MLIR. The only difference is that those are unique functions, so you can have captures if you want. And if you do not create a parser and a printer, then you can have a default parser and a printer, and it will just parse each attribute one by one. And this would be the default format, so this is exactly what we want. Then when we have all this information, when we can create this new type in this dialect. So we just create what's called a dynamic type definition with the dialect, the name of the type, the verifier, the parser, and the printer. And we can give it to the math dialect, which will add it with the add dynamic type. And this allows us to already pass the one function like this. So we can already use this complex type in MLIR directly. So now we want to show how to define a new operation, which I call makeComplex. So we need to write a verifier, because all operations have verifiers mostly. And so here, makeComplex takes, as I said, 2 arguments and will return complex number. So what we need to do is first to check that we have 2 operands and 1 result. And what we need to check is that the result is actually a dynamic type. So we can use a dim cast with dynamic type to check if a type is a dynamic type or not. And then we can just get its name and check that it's the name of the type we expect. So here, math.complex. But if we want, we can also use the definition we defined earlier to check if it's the right definition or not. So those things are equivalent. We can either check that the name is correct or check that the definition is the right one. This version is, of course, a bit faster since it uses type IDs in the background. And we then check that the operands actually have the same types and that they have the same time as the parameter of this complex type. And this is, for instance, how you would write a verifier for this operation. We can mostly register operation the same way we did with the type. So we have a name, we have now the verifier, we can create a printer, we can create a parser, the exact same way you would write it in MLIR currently, beside that there are STD unique function, LLVM unique functions. And then we can use this dynamic up definition, we create one, and we add it to the math dialect. So with just this code, we would be able to, we would add the makeComplex operation to the math dialect, and with what we had before, we can now fully parse a function like this. So everything was done in runtime. By that, I mean that you can actually change the behavior at runtime of the compiler. And we can also add traits, for instance, if we want to the operations. So we can add existing traits that are already defined in C++ by using the getDynamicTrait function. So here we would take a list of traits that we want to create a list of traits that will be satisfied by the operation. And we will add this existing trait to the list. And we can add it to the operation when we add the dynamic operation. We can just add the traits as argument. Yeah. We can also define new traits at runtime. So this is something that actually comes from the implementation, is that if we want, we can define a new trait at runtime by just giving it a unique function that represents the verifier. So for instance, here, we could create a trait that checks that there is exactly 2 operands. And we need to register it in the MLIR context that will take care of owning the unique function. And we need to give it a name. So here we call it like pair operand trait. And we can add it to we can also add it the same way we did as before to the operation when we create it. So we can only add the traits when we create the operations. We cannot add them after the operation was created. We can also add interfaces to operation, mostly in the same way. So if we take the memory effect interface that is defined in TableGen, so we have like one method that has returns a void, and that name is getEffects, and that contains a list of effects as parameters. We can define an implementation. We need to define an implementation for each method when we want to add an interface implementation to an operation. So here would create a getEffect function that will just return this list of effects. So if we want to add it into our make complex operation, we actually do not need to add any effect since the operation is pure. So we don't have to write anything in there. And then we can just create this. So the interface implementation by just giving all the methods that we need, so which is only the getEffects. And just note that this structure would be generated by TableGen, but I'll come back later to it. And then we can do as we did with the traits. We can give a list of interfaces when creating a new operation. So here, during the operation creation, we can actually add the interfaces after the traits. So the interaction with the traits and interface on dynamic operations and dynamic types works the exact same way as you would do with C++ defined operations and types. So you can check if an operation has a trait or not by giving him the concrete trait. And you can check, and you can try to check if an operation has an interface, is implementing an interface or not. In particular, this means that we can actually reuse generic passes. So for instance, if we give this function in MLIR, so here we're just creating a new complex number, but we're never using it. Since we specified that this function was pure, then when we use canonicalize on this MLIR module, then it removes the operation as expected since it has no effects. So for completeness, operations can actually define 2 more fields. When you can define them in, for instance, C++, you have the folder hook and the canonicalization patterns. So when you want to define an operation at runtime, you just giving them this, and those are unique functions of the exact same function you would generate from your C++ code. So now a bit of background on how everything is implemented, maybe. So in MLIR, so each C++ class can define at compile time a unique type ID. And you would get it this way. So when you have a C++ class, you get a unique type ID defining this class. So in MLIR, the type IDs are used to uniquely define operation, types, traits, interfaces, and dialects. So whenever you call is a function, for instance, is a function, then what it does in the background is that it just checks that the type ID of the operand of the operation is equal to the type ID of the concrete operation. when you add an operation in MLIR, it will directly get the type ID. It will give the type ID to the real add operation that exists in the dialect. So if we can generate new type IDs at runtime, that's how we can define new operations, because the type ID will identify this newly defined operation at runtime. So the way we can actually define type IDs at runtime is by just taking the address of an allocated object, because that's how it actually works in the type ID implementation. So if we malloc something, taking its address should be a unique type ID. So we can create something called the type ID allocator that has a vector of storage that basically represent the type ID values that are hidden from the users. And to allocate a new ID, we just have to create a new element, malloc it, and get its address. So we can add this thing in the MLIR context to essentially create new type IDs at runtime, which allow us to create new operations and new type at runtimes. So for the registration of operations, as I said, so we need to open the MLIR API a bit, which is already done through multiple patches. And the way this works is that whenever you want to add a dynamic operation, what you essentially do is that you use the add operation function you have in the dialects and allocate a new type ID, and then give all the verifier, the parser, and everything I defined before. And to add dynamic dialects, this is essentially the same thing. And this is also the same thing for the traits. But the types, however, works a bit differently, because all types need to define a storage for parameters. So in our case, what we do is that the storage of a type is the type definition. So this is what we define at runtime. It contains the parser, the printer, the verifiers. And it contains the list of parameters, the list of attributes, which is the parameter of the types. And the dynamic type is essentially just a type, but we give it different type IDs depending on the type definition. So whenever you create a new dynamic type, essentially you're going to register the exact same type, but with a different type ID. And the interfaces, however, works a bit differently than everything else. So in operations, dialect, and types, the interfaces implementation are inside what's called interface map, which is essentially a map between type IDs and void star, which represent the void star represent the interface implementations. So the void star elements are like struct or function pointers, and each of the function pointers represents one method that the operation, dialect, or type needs to implement. They're often called in MLIR model or concept. And how they generated is that when you have, so this memory effect interface defined in TableGen, whenever you launch the TableGen generation, it will basically create you a new struct, which is the new model, which contain the different methods that needs to be defined. So the problem in our case is that we cannot just use this thing to implement or interface methods, because this is a function pointer, which means that we cannot encode all runtime information we could, because we might need, would like to use basically unique functions. So the last time I asked, I think I understood that basically it was not possible to change this in MLIR, to change this function pointer to unique functions. So basically we needed to find a workaround to make this work. So the idea would be that every time you have this TableGen definition of an interface, what we would do is that we would also generate the model we want, which is using a unique functions. And then in the original model, what we do is that we redirect it to this model with a unique function. So every time you want to get the method from an interface, what it would essentially do is that it would redirect it to the right model that contains all this runtime information that we want to carry. So in summary, this project would allow us to define new operation types, traits, dialects, and make them work with the existing passes that are the ones that are generic and that use essentially only interfaces and traits. You can also technically define your own passes that use these dynamic types and operations, but then you would still need to know the name of those operations and types. And this approach, if you combine it with proper Python bindings, should allow user to essentially extend the MLIR compiler directly from Python without recompiling it, which is pretty strong on that, and which make the life easier for a lot of users, I think. And that's it. If you have any question, feel free to ask me.
Thank you, Mathieu. Great luck. Let's move on to questions then, and discussions. I'm sure there are, I know many people online that will be interested by the possibility this would open up. Yeah, John, go ahead.
So based on your but there was a discussion on Discourse 2 weeks ago about related to introspection of existing types.
Yes.
So your dynamic types would allow introspection.
I'm not entirely sure, because I mean, you could technically get back the type definition, but they're still hidden. I mean, there's still unique functions in it. So you cannot introspect how the verifier works, for instance.
Right, but what I'm talking about is introspecting on the parameters.
On the parameters, yes, because here there would always be attributes.
Right, right. In your experience, would that be feasible or useful to have for even types defined in TableGen?
Like
the basic, built-in types, for instance.
So you mean that the basic built-in types would have this format, so you can basically get easily the operands.
Right, right. So any type that isn't defined with entirely with attributes,
yeah,
and other types would be, you could introspect from Python, for instance.
Yeah, I mean, that could make sense. I mean, that would change a lot of things, I think. But so technically, you can put arbitrary data in attributes, right? So you could have all types having only attributes.
Yep.
But that would change a lot on MLIR, I think.
Yeah.
But yeah, that would be like very helpful for a lot of people that want to I mean, on projects where I need to introspect types, this is currently, you need to write each case for each different type. So yeah, that would be very helpful, I think.
Okay.
But I mean, there's still one possibility, which would be to define an interface that would get you, I mean, for each type, you would define an interface that would return you a list of attributes. That would work too, I think.
For any type defined entirely with attributes and other types.
Yeah.
Yeah. Yeah. But that's essentially dynamic types.
Yeah, that's essentially that. Yeah, mostly. Yeah, exactly. Actually.
What is? And if anyone else has a question, feel free to jump in. But what is the performance of this compared to, natively C++ defined types and attributes?
So I haven't looked at it in detail, but I mean, I haven't looked at it at all. But in terms of the implementation, whenever you retrieve an interface, it will be slightly slower because you need to have one or two pointer in direction. But if your interfaces have a lot of work to do, that should be negligible. And otherwise, whenever you want to get a type or you want to get an operation, you need to do it at first by name, but then you can use a type ID inside, so it should be the same speed, basically.
Just to interject on your estimation on the cost and interface, the cost of retrieving an interface is usually not significant when you match on the interface. It's when you miss because what you frequently may do is like walk all the IR and do something on an operation that implement the interface. But you pay the cost of looking up the interface on all of the IR, including all of the operations that don't implement the interface. And so those costs usually show up because you may have one or two up in the whole IR that will implement the interface, but you will still do the lookup for 1,000 times.
Okay. So in this
you could
case,
have an analysis that caches that, just if it was really a concern. Just walk once, build a map of all interfaces, and if necessary.
Sure, but that's only useful if your pass will iterate multiple times, right? Well,
Yeah.
they are, right? Yeah.
Or you can preserve it, right?
So what you
Anyway,
mean? Okay. So maybe what you meant is that basically in my case, it wouldn't have a cost, much of a cost, because it wouldn't change when you miss.
I don't know. Would it change when you miss?
No, it
Don't you
wouldn't.
need to do the lookup?
So the lookup goes, so when you match on an interface, whenever you want to get the method, what it does is that basically the function, the method itself, will just look up somewhere. And this lookup is like instant. It's just like 1 or 2 pointer dereference. And it only does it
you
when
haven't
it
modified it's not in the dincast to the interface. It's after the dincast succeeds.
Yeah.
Okay. Yeah, that makes sense.
Essentially, in the internal representation, the interface map is exactly the same. It's just what it contains is a bit different.
So are there plans to bring this up in parallel with the Python bindings? Just to make sure, the design goes hand in hand and everything.
Yeah, I haven't looked at the Python bindings yet, but that would be one of the objectives. I'm soon done writing all the patch for that, and I think that working with the Python binding should be the next step, I think.
Awesome.
Because I heard a lot of people that are interested about this.
Yep.
And that requires developing a strong C API, which will help other languages as well.
Yeah, I'm often citing Python bindings because I see that there's a lot of interest in there, but there's definitely other languages that could be interested in that.
Yeah. For instance, Swift. Mehdi's smiling.
No, yeah, indeed, because with this project, I was thinking about you and about Swift. So yeah, I'm glad to hear that.
Yeah.
And I think other people would want to use Haskell to write some compiler passes. And who knows? Maybe they're gonna define their dialect in Haskell and everything. It's gonna be interesting.
In your opinion, would it make sense to define everything like this?
So it's harder to look up something because right now you have a C++ class, so you can easily know what's defined and what's not defined.
Mm-hmm.
And that's kind of one of the only difference.
I guess the question when we say defining everything this way would be even if you have a C++ class, the C++ class could be registered using the same mechanism internally, right?
Yep.
Oh, okay. It could make sense. There's no... Okay, so there is... No, I think it could make sense because you would still be able to define custom functions on the C++ class, which is one other thing that is currently missing because, yeah, you don't have C++ class. It could make sense. Because there's not so much cost at defining everything at runtime. So, yeah. But essentially, defining everything at this way would be essentially defining it how it's defined currently in MLIR, because I'm reusing a lot of the API of MLIR.
Yeah, I was going to say, I think basically other than sort of the fact that you have a C++ class you can get a type ID for all these things, this is you can almost think about this as like a refactor of, the various APIs. Actually, that's the question I was going to ask. Like, can we just drop the dynamic and just call it like, this is like the new better API for, adding operations?
Yeah, we could. I mean, I called it like dynamic op because at some point I wanted to simplify things by having just a structure that contains like the list of traits, the different interfaces. And then whenever you want to register it, it creates the right function, like the as trait function or things like this.
Yeah, and then I guess the question would be like, then we can kind of decouple it, like we can have like sort of like the C++ sort of sugar that is like has the dynamic type and things like that. And then that's like none of those are like methods on the context or known to the core in really any way. It's just they're clients of this like better API.
Yes,
maybe the same API.
The only thing that changed is that you need one or two data structures on the MLIR context because you need to store like everything that's defined dynamically, basically. So it's either defined in the MLIR context or in what I call the extensible dialects.
Okay. So that's like besides the type ID, you basically need an owner of the unique function.
Yeah.
Yeah. Okay. Yeah.
Or you could have everything as a STD function, but that's, I mean, in terms of performance, that might be not good.
So do you, I guess I was going to ask, it would be really useful in the RFC if you went over the specific indirections that are added by this system and just sort of make sure each one has sort of like a rationale. Because I think if we can kind of pick through those and brainstorm, if we can get it down to, no additional things, which I think for the core APIs should be possible, and everything else that introduces an indirection would be a client of those APIs, then that'll really help us to understand, where we're paying a cost and why.
Yeah, I can definitely like make a list of all indirections.
Awesome. Yeah.
That's also key to understand the unification aspects, right, between static and dynamic, understanding those costs. Because that would be a blocker. Like I think we wouldn't want the C++ code to become slower by changing the way
I mean, mostly the main difference is that if whenever you have a function pointer, you change it to a unique function, then it would be the same. I think the costs come only from the unique function, and the registration might be a bit longer, I'm not sure.
Yeah, this definitely sounds like something that we'll need to stare at patches and kind of read over in the RFC and digest, because it's a pretty detailed discussion.
Yeah.
Awesome. Yeah, this is actually really awesome, and I'm really looking forward to being able to, run, write my dialects in Python or whatnot, or add new things, especially on the Linux side. I think that could be a really cool starting motivator. Maybe we could even get rid of all that, YAML stuff we have checked in and everything. It would just be like, okay, here's some Python code that generates it all.
There's a difference though, like the YAML thing that you have right now for Linux, for instance, allows you to generate ODS, which allows you to have C++ classes, right? The problem of defining your dialect in Python is that then you don't have C++ classes and you cannot write C++ paths. So when you write a dialect or operations in a language using those bindings, it kind of ties you to write your compiler or at least the passes that operates on this dialect in this language.
Yeah, we have I guess I was talking from the MPComp perspective. We would probably use this because we're planning on, like, for example, all of the Torch ops, they have they're pretty polymorphic. So it's like, oh, this thing is optional and all this stuff. And so Stella and I were thinking about actually writing some Python code that then we would kind of lower into Torch script, but that Python code would allow having inline Linux generic operations, things like that. And so those sort of inline operations, those would be really useful too. That would be one way to make it convenient to bring those in. yeah, I think there's a lot of useful abstractions that are enabled by this.
There's maybe one thing I should add that I didn't mention, is that the way everything works, you cannot use the dialect registry in a good way, because you need to first register the dialect to be able to add the dynamic types in it. So that's just some cost to know also.
I didn't follow that.
So basically, to be able to add a new dynamic type on the dialect needs to be already registered.
And like
In the
registered and loaded in the context?
Yeah.
What's the relationship you said with the dialect registry?
The dialect registry that is used to load the dialects lazily.
But all those APIs are already dynamic, right? Like what part of that is static?
So, I mean, right now, if you just look at, let's say, MLIR, I mean, it's just a question of like, you need to first load the dialect to be able to add dynamic operations, dynamic types to it. So if you have a function in MLIR like MLIR opt main that just takes dialect registry, you cannot register your new operations and types because the dialects are not registered in a MLIR context already, loaded in the MLIR context.
Right. I guess what you would, I see what you mean. It's like what you would want is a hook to say is like, if these dialects ever get loaded, then you need to only then define the dynamic operation in it.
Yeah.
Right. That's what you would want. It's like on dialect loading callback.
Exactly.
That can be added also. A listener on this event. Makes sense. I think so. If I don't know if you followed channel orders, the problem is that when you start running a pipeline, a pass pipeline, for instance, dialects gets loaded by dependency of passes.
Okay.
The problem is that if a dialect is a dynamic one, it only gets loaded now. But when are the operations on type added?
Yeah.
Right.
Yeah. So really,
there's
it's
no callback.
Define my dialect, and then put that whole thing inside of like when you need the dialect to run all this code.
Exactly. So you need a callback to. Yeah. Steven, you wanted to ask something else.
I was going to go back to Mehdi's comment that about you're being stuck in the language that you write the dialect in, and I think today, kind of from a conceptual perspective, what the C++ classes are doing is providing an introspection mechanism that's static. And so when you have a C++ class, you also statically know all of the fields that are part of that class. And so it's easy to write a transformation against it. And the piece that's missing is a dynamic introspection where you can say, for a dialect, give me all the operations. And for an operation, give me the names of all of the arguments and give me the names of all of the results. And that if we had that kind of dynamic introspection into a dialect that you could get this cross-language kind of thing where you wrote a dialect in one language and you could introspect it in another language and write a pass against it.
Yeah, it's kind of like how we have operation. Operation, you kind of generically walk it, all the regions and all the operands and results and attributes and stuff. But like for types and dialects, we don't have that type. And like sort of like the kind of abstract operations, so to speak, we don't have any similar sort of APIs, I think is what you're saying, Stephen.
Yeah.
And yeah, I mean, I think a lot that I'm aware of. Yeah, like I think one interesting thing here would be well, for abstract operations, it's a little bit different, but like for types, a lot of types can be expressed with like an ontology of, lists, dictionaries, and, integers and floats or something. And so, coming from the Python side, it's like basically every language has some analog to that. And so, we could kind of have an interface which sort of says my, my type or attribute or whatever has a storage which is represented with this kind of standard ontology, and then it probably wouldn't be as performant in some cases, but it would allow a lot of that cross-language behavior. It's basically like would be kind of like a JSON sort of description.
And we
I can
already
imagine even in some cases you might want to do things like in Python, ask an operation for its documentation, or something like that, which is kind of a very literate programming kind of thing.
Yeah.
Anyway, just a wacky idea.
That's a very good point. For structured type, what I call structured type, which is this standard ontology that you mentioned, Sean, I think we did a step in this direction when we added the way to generate types from table gen, because we support a specific set of fields to organize types. And that was the idea. The idea was like, well, in C you have structure, and you can define a new structure. Why aren't type just the same way aggregate of other primitives that MLIR knows about?
Yeah, I think the difference here is that the ontology doesn't extend into runtime. It's a purely static ontology. And so there's no way to be like, type dot, storage dot, like, what's the first layer of the storage? Like, is it a list?
We don't generate the introspection. Yeah, we don't generate the introspection and dynamic accessors for all of that, but we could, and probably we should restructure all of that. I would love that.
Well, it also supports the arbitrary types, not just other types and attributes.
Yeah.
What do you mean by arbitrary types?
Like string ref, for instance, array ref, that kind of stuff. That could all be translated into, manually translated into the equivalent types and attributes. But as of now,
yeah, I think that was my primary concern with that distinction is, it's very kind of array refy, string refy, rather than like array ref of type. Well, it should just be like a list of types. But I mean, I understand it was done this way, probably for some compelling performance reasons.
But you can overlay you can overlay an introspection on top of that. An array ref of type is just you can expose an accessor which becomes an array attribute of types, and with attributes like you should be able to.
Well, you can use a custom C++ class. So like in Circuit, we have a struct type which refers to a C++ class, and that's one of the parameters.
Yes, but then you're outside of the standard ontology that Sean was talking about, right?
Yeah,
I get it. The other thing that only using other types and attributes gets you is you don't have to worry about memory management and cloning into the standard heap or whatever.
Yeah. Although that is a little bit of a deliberate design decision. It's very heavily based on interning and the bulk allocation of array refs and stuff. So like if we just malloped up a big object graph of lists, dicts, and heap allocated individual integers and floating point numbers, that would have a pretty different performance profile. I mean, like, again, if like you're accessing this from Python, then like that's what you already have by default, so it's like not an issue. But I guess in principle, there's like a class of C++ users of MLIR that have some concerns with that.
In principle?
I'm just saying, because it hasn't really been measured. I mean, I think we all kind of know it would suck, but
to come back on Steven's comments earlier about the introspection. So yes, we could generate also introspection field in the same way on operation. But when we write transformation, how would it look like with interfaces, for example? If someone now defines an interface in Python, I think we would have the interface only by name attached to the operation with this dynamic definition. And it's not clear to me from C++ how you could match this interface or use it or invoke method on this interface.
Yeah, I mean, I think that we need to distinguish the cases of the binding code is trying to interop with the C++ passes and just the binding code has its own kind of like little world that it wants to be self-consistent in. And indeed, like, yeah, we would have to do something like Mathieu's like memory effects dying interface, or some sort of something that knows how to sort of launder that across the binding boundary to get those to make those things actually work by type ID rather than by name, by class, static type ID rather than name. But I think, yeah, we would have to probably like ODS generate some sort of binding code for that. Basically just exposes like the type ID of like memory effects off interface.
I think it would definitely look very different from the static dispatch that we have today. But I mean, I think it would, I don't see any reason why, if we can raise the dynamic kind of dispatch into Python or some other language, that we couldn't have a dynamic dispatch API in C++. It's just awkward and nasty. Right.
Yeah.
To me, that's part of the elegance of MLIR, is that you kind of always have this underlying dynamic dispatch mechanism, but you have a static view into it. So it's kind of the opposite of Pythonic. It's C++ plus ick, which should be a word, I think. But it kind of gives you this nice statically typed view into the dynamic world of dialects and operations. And if what I see sort of Mathieu is doing is sort of giving you the dynamic view into what is fundamentally a dynamic dispatch mechanism underneath the hood anyway.
Yeah.
Which is why it's easy. And on almost all cases pretty easy, right?
I think that's a very good point to formulate an MLIR like that. It's yeah. I think you nailed some aspects of the philosophy in the design here.
Yeah, that's a pretty good insight. One other thing I'll mention is, there is actually another option for the bindings, is that you can have, to the extent that you have like you're building your own little world of things that eventually you translate into that like MLIR in Python, and then kind of you pass it on to like lower levels of the compiler stack or something. It is also an option to just sort of have a Python class called operation that has a list of operands, a list of results, and it's going to be less efficient than the C++ one. But it is an option to just write an MLIR analogous thing at the Python level and then translate it across the boundary as needed. So because most of the work there is really just defining the APIs at the Python level for how do you define a type or an operation or whatever. And the actual details of the actual operation class or the storage and stuff is not, barring maybe an efficiency aspect, it is you could do all that at the Python type level too, and then translate it into MLIR as well. I think that might be an interesting option for code bases that have like a lot of stuff that they are they're doing a huge amount of compiler work that's like sort of disjoint from the C++ code. You just need a way to launder it across the boundary, basically.
I think there's another way of viewing this also, which is that if you had a binding of this dynamic mechanism into MLIR, then it essentially becomes an MLIR schema. And so instead of just having untyped or unregistered MLIR with an unregistered dialect, you could have an MLIR schema section at the top of your file that says, here's all my operations and here's what they mean, and on the fly have parsers and printers that work with your otherwise unregistered dialects. because you can register them on the fly as part of the schema and then get all of the type checking and pretty printing and pretty parsing in the rest of the file. And basically what the C++, if you did that, then you can now specify all of your dialects in MLIR and build MLIR Inception, where we get rid of all the table gen, and there's just a tool that takes your schema and generates all of the nice C++ static typing for you.
That would be interesting. Like it could almost be like an ODS dialect, and then
right.
I mean, it might not be exactly ODS, but something like that. We would lower ODS into this dialect effectively.
I don't understand how you get pretty printing and parsing and all that kind of stuff, given that it relies on code written in function pointers. Unless you can do that declaratively.
That's what you would do. It's like you could use something similar to the declarative assembly in ODS, except that we would be able to interpret it at runtime. And
I would prefer everything be written declaratively.
Kind of ODS dialect. I think Mathieu, you played with those kind of thing as well.
Yeah. That's kind of the reason why I'm making all these things dynamic, is to build kind of something like this. But awesome. You start having problems when you want to interact with MLIR defined types. Exactly for the reason, you cannot, whenever you want to pass something like a vector, for instance, then you need to be able to introspect what's inside a vector. And you cannot do that because that's in MLIR world, C++, and things like this.
Yeah.
You kind of need the equivalent in table gen of these sort of primitive definitions that are, sort of base all of the declarative definitions get sort of based off of, right? But they're primitive, and the table gen system kind of knows about them.
Yeah.
So only partially related, one of the problems we're having in some Python bindings I'm working on is that the C++ builders and other accessory methods on operations have a lot of logic in them that I simply can't access from Python at the moment. So especially the builders are what we're worried about. So, inferring types from, the arguments is kind of a critical thing you do in operation builders. So based on your experience here, what would you suggest? We have a few ideas, but.
So that's essentially trying to replicate what ODS is doing, right?
Yes.
Because, if it's done in ODS, it can be done somewhere else with the same code, right?
Well, the builders generally declare their function signatures, their method signatures.
Yep.
And then the bulk of it is in C++.
Yeah. So, if it's written in C++, you need to, I think, rewrite it in Python. I don't see... if you can't write it declaratively, there's, I think, no way to, have it in different languages, right?
Well, but we could have some kind of function pointer or automatically generate the C API to call those builders in C++.
Yeah, that would make sense, I think. If you generate the code, you can generate Python bindings with it, or any bindings, actually.
Right. That's our current, plan, long-term plan.
Yeah, I will mention, that's sort of actually one of the reasons why we sort of, we haven't pushed on that nearly enough, like where the shape dialect came from, because it's like we want to be able to express shape constraints in one way, and then have it generated and consumed in multiple different spots. So at the moment, like the hook in with the builder is sort of a little bit custom, but that's one of the things where we want to have. We haven't actually, like I said, that needs a lot more work. But that's sort of the same thing where you describe it in one way, we describe the constraints, in one place, and then the different consumers could be generated. Because like we have the same problem. We have the ops that need to be type checked in Python. They need to be type checked at creation time and at shape refinement time and at execution time. Well, execution time is sort of optional, but today that happens. Another thing there is to actually reify and hoist, so we don't do it while executing the ops or kernels, however you want to phrase it, but we can do it ahead of time. But yeah, I agree with the thing where it's like if it's in C, we can re-execute it, but it's not as nice as being able to just declare it and use it as a source for the different spots.
Yeah, because sometimes, especially like I guess the shape refinement case is a really good example, because there you want to also do a data flow analysis on it, and so there it's like you're not just literally executing it; it's like you're actually executing over a lattice, and then that is that does require some analysis and to reformulate what is like literally written to be executed in form of a data flow transfer function.
Yeah, and there also different folks may want different analysis, and so that's where
Yes.
like I just care about static. Well, okay, there you go.
Yeah.
Or I care about equality, blah blah blah. So yeah, very good point, Sean.
All right, I think we're out of time, unfortunately. So next week we're gonna have a talk about types and attribute. Mike, if you're online, maybe you can give us a 2-sentence the topic for next week.
Yeah, we're going to be talking about, I guess, how to support type defs. And MLIR is the 1-sentence summary. It's something that we've been looking at in the circuit project because System Verilog has type defs and we want to do them justice. So we're trying to figure out how to make that work in our compiler.
That's good. Thank you. And thank you, Mathieu, again for the talk and the walk here. I think it's a very exciting direction for MLIR, and I'm looking forward to that.
Really nice work. I look forward to the Python bindings.
Yep. This is awesome.
All right. Thanks, everyone.
See you.
Bye.
Bye.
Bye.